All right, geometers, welcome back for another riveting day of learning from home. So today we're going to continue talking about Chapter 11, Section 1, which is similar polygons. And today's focus is not on, if the polygons are similar or not, but once we know they're similar, we want to determine missing angles or side lengths. All right, and that's today's focus, is just solving for missing values in similar polygons. So recall from yesterday, the definition of similar polygons states two things. One, that the corresponding angles are congruent, and two, that the corresponding side lengths are proportional. And again, proportional means in the same ratio or same fraction. So using this definition, we can solve for missing sides and angles in similar polygons. And here's how we're going to do it. First step, pay very close attention to your similarity statement. That's really important so that you can tell right away which sides and angles correspond to one another. All right? Next step. Solving for missing angles is really easy. If missing angles are congruent, as in the definition of similar up here, then that simply means they're going to have equal measures. So if you know one angle's measure, you know its corresponding angle has the same measure, and that's simple. Solving for side lengths is a little more complicated, and we have to do this by using proportions. We know from the definition that if the polygons are similar, then the corresponding side lengths are going to be proportional. So what we're going to do is first establish a similarity ratio, and that's a ratio of the sides that are known to us in the two polygons, and we'll use this to set up proportions to solve for the missing side. So that's our game plan. We'll just do a couple examples, and hopefully it'll make sense to you guys. All right, so in this example, I'm given that triangle ABC is similar to triangle QRS. Now notice I have them drawn for you in the same orientation, and that just makes it easier on you. That won't always be the case, but you can see that the corresponding sides are in the same location relative to the triangle with how they're drawn. But because that is not always the case, one thing that I do is I use my similarity statement right away, and I mark my triangles with the corresponding sides marked. Now, there isn't really a textbook way to do this. With congruency, we use congruency marks. So I've come up with my own system, and my own system is just by using a certain number of dots. So for instance, in my similarity statement, side AB will correspond with side QR. So I'm going to put one dot on AB and one dot on QR. And I know that BC corresponds with RS, so I'll do two dots for those. And then I know that AC corresponds with QS, so I'll do three dots. Or I could have left that one blank, doesn't matter. Just some way for me to visually see which sides correspond. So, to establish my similarity ratio, I need to find two sides that correspond that are both have given values or numbers there. So like 12 and X, no, they're both not numbers. 10 and Y, no, they're both not numbers, but check it out. 18 and 12, those are both numbers. So I'm going to establish my similarity ratio. Now it's important to write it as it is asked. So it says to go from triangle ABC to triangle QRS. So I need to go in this direction, which makes my similarity ratio 18 to 12. But that simplifies when you divide both by 6 to 3. 3. Erase. Well, I can't get it to erase for some reason, but that gives me a similarity ratio of 3 to 2. You guys could tell from home I still have the same trouble I would in class on my little smartboard thing. All right, now these first three are angles. This is going to be really easy for me to do. All right, I don't need my similarity ratio to solve for angles. I just know that corresponding angles are congruent, so they're going to have the same measures. So if angle Q is 50 degrees and it corresponds with angle A, then this little variable A would be 50. So A is also 50 degrees. All right, I guess I don't need the degree symbol because it's already there. All right, and here we go. So B, I'm looking for B. Now, angle R in my similarity statement corresponds to angle B. So if this is 60 degrees, then so is this. So B is 60. And then finally for C. Now in this case, you'll notice I want to find a C, and it corresponds to this angle S right here. But there isn't an angle here. So in this case, what we're going to have to do is, you can't forget the things we already learned, and that's the triangle sum theorem. And all the angles in a triangle add up to 180 degrees. So if this is 60 and 50, that's 110, which leaves 70 degrees for C. Sweet. So the angles were super easy. Now to find the side lengths. This, like I said, is just a little bit harder because we have to do it by using proportions. And the way we establish this is by using my similarity ratio. Remember, my similarity ratio is from triangle ABC to triangle QRS. So when I set up my ratios, I want to set it up with the parts from ABC on top and the parts from QRS on bottom. Now, the similarity ratio from ABC to QRS was 3 to 2. I established this already. And now to solve for x. Well, x is part of triangle QRS, so it's going to go on bottom. And the side length that it corresponds to it in triangle ABC is side length BC, which is 12. So I got 3 over 2 equals 12 over x. And I'll solve this proportion by cross multiplication. I'm going to get 3x is equal to 24, so x is equal to 8. And again, the units are already there. When I substitute, it will give me 8 inches, so it's unnecessary. If you put inches, not a big deal though. All right, now I'm going to do the same thing to solve for y. Now again, I'm going to establish my similarity ratio as 3 to 2, and that's from this triangle to this one. Now y is a missing side length in this triangle, so I'll put y on top, and it corresponds to the 10 in this triangle, so I'll put 10 on bottom. And again, I'm just establishing that because y corresponds with 10, and I'm going from here to there. Now when I cross multiply, I get 30 is equal to 2y, so that gives me that y is 15. So I know that y is 15, and when I sub that back in, I get 15 inches. So there you go. We solved for missing angles and missing side lengths. We'll do a couple more examples just to show you guys what's going on and make sure you understand. So in this case, this time we have, rather than similar triangles, we have some similar quadrilaterals. And you also notice that in the similarity statement, just like with the transformations unit that we did before, we use prime sometimes to indicate which variables correspond. And that makes it much easier to see which parts correspond. So I've got a similarity statement saying quadrilateral ABCD is similar to quadrilateral A prime, B prime, C prime, D prime. So, again, the first step is to establish my similarity ratio. And I'm going to start by putting dots on my corresponding sides. So, AB corresponds with A prime, B prime. And BC corresponds, so do 2 dots here for BC, and it corresponds with B prime, C prime. All right, let's see. And we got CD, do 3 dots there. It corresponds with C prime, D prime. And then finally, AD is going to correspond to A prime, D prime, and I'll just leave that one blank. And the blank sides will correspond to one another. So I'm looking for 2 corresponding sides that both have numbers. And I find that it's the 2 dots, BC and B prime, C prime. And we want to know the similarity ratio from quadrilateral ABCD to A prime, D prime, A prime, B prime, C prime. So I'm going to go in this direction. So it's 2 to 3. Which simplifies, or excuse me, 2 to 6 rather, which simplifies to 1/3. Not sure my eraser is not working. That's really weird. All right. Anyway, so we have our similarity ratio, and now I can solve for the missing side lengths. All right. So for AB, AB is 1 dot. Right. I'm going in this direction. So the similarity ratio is 1 to 3. So 1 over 3 is equal to AB over the 1 dot. It matches up with 21. And when I cross multiply, I'm going to get 3AB is equal to 21. I'm going to divide both sides by 3. I get AB is 7. Then for CD, again, I'm going to use the same similarity ratio of 1 to 3. 1 to 3, 1 to 3. And CD is in this quadrilateral, so I'll say 1 over 3 is equal to CD over 12. 3 dots correspond. When I cross multiply, I get 3CD is equal to 12. That gives me that CD is equal to 4. And then the last one here is A prime, D prime. And in this case, you'll notice that what I'm missing, or what I'm looking for, is in this quadrilateral. So I'm going to put it on bottom. Put A prime, D prime on bottom. And on top, what corresponded to it, that blank side, was the 5. And this time when I cross multiply, I get pretty directly. 1 times a prime d prime, is a prime d prime, and 5 times 3 is 15. Cross multiplication, I get those side lengths. All right, now for the angles, the easy part. All right, so B corresponds with B prime. That's got to be 100 degrees. Easy enough. So the measure of angle B is 100 degrees. A corresponds with A prime, so they're both 60 degrees. Easy enough. All right, measure of angle C prime. Well, C prime corresponds with C. They got to be congruent, so they're both going to be 90 degrees. I'm not sure what happened there. Let me fix that. Sorry. 90 degrees. Again, not sure what happened there. Let me try that again. Much better. All right, and then finally for D, notice that D and D prime are both blank, but that's not a big deal because I can figure that out by simply saying, hey, in a quadrilateral, all the angles add to 360. Well, 60 and 100 and 90 is 250 degrees, so that leaves 110 degrees for D and D prime. And finally, the perimeters. All right, so you guys, in this problem, we solved and we know that AB is 7. We know that CD is 4. So when I add all these side lengths up, 2 and 4 and 5 and 7, I get that the perimeter of ABCD is 18. All right. I also notice that in this one, I solved for A prime D prime, which was 15. And when I add this up, I get 54. So the ratio of the perimeters is 18 to 54, which also simplifies to 1/3. Now, will always be the case. The ratio of perimeters will always equal the similarity ratio. Sweet. All right. And I think there's just one more example for us to do.